Hello, welcome everyone. We'll get started in just a second. Probably on 4:32 we'll get going, but just letting everyone join in quickly before we do get going. If you have any particular areas of Mod 5 your weekend you want us to focus on, put them in the chat, or in fact just put anything in the chat. Put a W, say hi, get the chat going. But we're getting going at 4:32, as I said. We'll be covering the whole of Mod 5 in the next 2 hours. So strap in, have something to write with, make sure you are ready to go. And if you have questions, put them in the chat as well. We'll get through them as we go today. Okay. All right, so 4:32 we'll get going. Welcome everyone. And as I was just saying before, if you have any areas you want to focus on, put them in the chat. And we'll get going in just a sec. Okay. And cool, just before we get started, can I just do a quick check as well? Can everyone hear me? If you can hear, type a comment in the chat, say yes. Just checking that we can all hear. I'm getting celebration emojis. Okay, great. Thank you, okay. Thanks, Zali. Thanks, BC Clips. Great. All right, we're on 4:32. Won't waste any more time because I know a lot of you are assessments. Before I do get started as well, can I just get a quick gauge of how far away from assessments we all are? Can I get a number of days away from assessments? Everyone type in chat. Are we 2 days away, 3 days away, 5 days, 7 days, 10 days? How many days are we away from exams? Just so I know the urgency of everyone as well. Tomorrow, okay, let's make good use of this time. We've got one from tomorrow, Matali. Let's make sure it's use this time for as high yield stuff as possible. What about everyone else? In a week, got an assignment, fair enough. Two to 3 weeks, cool, so you're a fair bit away. Okay. 9 days, Jared, Jan, 2 weeks, Loki. Okay, so some of us have still a bit of time, which is good. I think this is a good time to be doing this review. Probably the best time of doing this if you still have just about a week and a half or more time left, because this will really expose a lot of areas you probably haven't fully understood or fully covered. And the ideal case is you go away from today and you have a lot to work on in the next essentially week to 2 to 3 weeks. But I think we'll get going. So 45 of us in here. If at any point today you guys have questions, put them in the chat. If what I'm saying doesn't make sense, ask a question, let me know, because it means I'm not doing my job. It means I'm explaining badly. Just shout at me in the chat and I'll go back and re-explain things. As I said as well, if you have areas you want to focus on, put them in the chat too. Questions, put them in chat, anything in the chat, and I can see it as we go along. I think compared to the last rapid review, the delay between the chat and when I can see it should be a lot shorter, so I'll be able to answer questions a lot more promptly today. But let's get going. So, Module 5, you guys all know this module already, equilibrium acid reactions, so I won't explain what the module is. But our job for today is to really get through all of this content one more time in a short window and expose all that you don't know. The way that we structure our teaching at Catalyst is we finished this module, we finished it in week 1 of this term. So everyone who did Catalyst had already finished this module in week 1 of term 4. And since then, we've just been doing questions the whole time. And we finished our exams 2 weeks ago. Our last sessions were just this last week. And essentially, if you are done Catalyst, you should be in a pretty good spot for your exams, whether they were this week or in 2 to 3 weeks' time. Now, if you hadn't done Catalyst yet, it's okay. This session is going to help recover everything, and if you want further help, we actually have a special offer for all of you. So if you want access to everything that you're seeing today, all these resources, plus our questions, plus our exams, plus support outside the classroom on our Slack and our drop-in session, you can actually get access to all of that for free if you are keen on joining us for Term 1 2026. And I know that a lot of you are actually already keen on joining us in 2026 for Term 1, which would be Module 6 for most of you, or potentially Module 5 for those of you going out of order. But for if you're here, you're probably doing Mod 5, so it'd be Mod 6. But if you sign up for our program next term, you get access to everything in this term from the moment you sign up. So if you were to sign up tomorrow, you get access to all of our resources, all the notes you see on the screen today, all the questions, all the support, as I said before. And that's just a special offer for anyone who's attended today. So if you're keen on claiming this, go to our website, submit a form, and say you're interested in joining, and we'll give you a call over the next few days to have it all sorted for you as soon as possible to get you resources, support, everything you need in these last critical few days before your exam. So that's pretty much the only thing I want to say before we get into the content itself. We're going to go through the 4 inquiry questions one by one. I want to focus more on inquiry question 3 and 4 in particular, given that inquiry question 1 and 2 are a bit more straightforward, but I really will pick out the important bits of those 2 modules that your teachers will most likely assess you on. And I'll just swap across to this view. Okay. So, Mod 5. We should know that at the very beginning of the module, your first inquiry question is static and dynamic equilibrium. And you would have talked about what these 2 are. You should know static equilibrium is reached when you have 0 rates that are equal, and dynamic equilibrium is non-zero rates that are equal for the forward versus reverse direction. You should know your reversibility of chem reactions case studies. So you have your burning of magnesium and steel wool, these are irreversible, and you have your cobalt chloride, hydration, dehydration, and iron nitrate, potassium thiocyanate as your equilibrium case studies. These can be given to you as just word sentences, and you need to be able to write the equations of these out. So the equations are all here. You have your metal combustion, you have your metal combustions, and then you have your reversible case study of cobalt chloride, split into 2 phases. Sometimes you see it written as one equation where it goes from the pink state to the sky blue state straight away, but in reality it's a 2-phase, 2 equilibria tied together. So just be aware of the 2 ways this can be notated. And then you know the iron thiocyanate case study as well. Of course, you have your full equation and then your net ionic. So know both, be able to explain what happens in terms of the colors, and explain what happens when equilibrium shifts left or right, now that you know how to explain that in terms of LCP and collision theory. Okay. Static dynamic equilibria, as we said already, the definitions are rates are equal for an equilibrium to be established, then static versus dynamic is all down to whether the rates are 0 or non-zero, respectively. An open or closed system, we should know as well. Can I get a answer in the chat? What's the difference between an open and closed system? Or can someone define an open system? Someone can define a closed system as well. BC Clips, the notes, these aren't available. These are only available to Catalyst students. You'll have them on the screen, so you can go back through the live stream and sort of watch them back if you want. But if you do want the notes, you can sign up for our program and you get them all for free once you've signed up. Yes, so open can have exchange with energy. Perfect. Tortoise, and I'm just going to say the names as they come. I don't know your actual names, so I'm just going to use usernames. And Metali, open can exchange matter, energy with surroundings. Yes, correct. And that is pretty much the open side of things. Then closed system, the difference is you can exchange energy, but you can't exchange matter. Why does this matter? Why do we care about open and closed system in the context of equilibrium? How does that relate together? Because that's actually what's important. That's actually what your teacher will assess you on. Why do we care if a system is closed or open in the context of equilibrium? As you guys answer that, if it's closed, how can it exchange energy? Because energy will still be able to leave. Closed system just implies you imagine it like a beaker that has a lid on it. would mean that you can't have matter leaving the system, but energy can still leave through the walls in terms of the heat loss that you can experience. So it's more just in terms of that. Yes, crazy cat dancer 5017, system can only reach equilibrium in a closed system, and that is the most important thing to realize from this dot point. So whenever you're talking about an equilibrium system, you're always talking about a closed system for both static and dynamic. The moment you have an open system, you can never truly establish equilibria because you constantly have loss of matter. The system is constantly being disturbed. Actually, constantly is probably not a good word, but it's over and over and over again being disturbed, and you can never come to a point where the system actually rests and the concentrations are constant, the rates are equal. So make sure you write in bold in your notes if you haven't already. A closed system is required for equilibrium to be formed, and an open system, you can never ever form equilibrium within. So this table sort of splits up the main things in terms of dynamic versus static equilibrium. In terms of what I already spoke about, the rates, the concentrations, whether they go to completion or not, the reversibility, the arrow used to notate them in an example. So I won't spend too much longer on this just because we're at the very beginning and we do have a lot to get through. The second thing to add on to static and dynamic equilibria is you should be able to draw a diagram to represent each. A static equilibria system is one where you show the reaction has gone to completion. So in this case, we have white and black dots notating the two reactants. Just make my pen a bit thinner. So white plus black is in equilibrium to make white and black. Or in the case of a static equilibria, the reaction actually goes to completion. And so you can notate that with a diagram showing that the reaction has completely gone to form these product molecules. There are none of the white molecules left. They've all been reacted and turned into the molecule form as the product. And that gives you a static equilibrium representation. You're showing that the reaction has come to rest. The rates of reaction are 0. It's reached completion. Dynamic equilibrium can be notated by showing a reaction that has only gone to partial completion. So you note here that we still have both of our reactants left, our reactant atoms, and instead in this second case, we no longer have a one-way reaction, we instead have a two-way reaction. So be able to notate both dynamic equilibria and static equilibria as diagrams. Very common exam question. It's 2 or 3 marks every time it comes up. Teachers love to assess it, so know how to do this and explain it in words what you're doing. The word explanation is just below in case you wanted to have something to go with that as well. Okay, and then I would argue the most high yield part from inquiry question 1 is actually the third dot point on Gibbs free energy. Well, all of the Gibbs free energy stuff from the first inquiry question, just because of how easy it is to forget this is part of the module once you've done a lot of the equilibrium, the calculations, you forget about Gibbs. So you should know this equation back to front. You've done it last year in module 4. You learned all about it. You should be able to talk about what enthalpy means. You should be able to talk about what entropy means, and you should be able to talk about how that can be related with temperature and put together in this equation to give you this thing called a delta G or Gibbs free energy and what that means as well, whether it's greater, equal, or less than 0. If you can't do that, this is an area I would focus a lot of attention on because this is almost guaranteed to be in your exam if you're doing Mod 5. It will be stupid not to go back and spend time on this. The dot point firstly asks about non-equilibrium systems. So this dot point is really in the context of Mod 4, making sure you understand what you've done in that previous module. Combustion and photosynthesis, you know they're both non-equilibrium systems, and you should know their equations. Combustion just being the reaction with oxygen, and photosynthesis having its own equation, which is all the way down here. So combustion, photosynthesis, know these two cases, and you should be able to construct any equation with combustion given it's just a reaction with oxygen. The balancing part is a little bit difficult sometimes. Just make sure you balance the single atoms on each side first before balancing things that have doubled up atoms. So Ruby, this This technically does apply for Queensland students who are doing equilibrium, but this is more focused at New South Wales HSC. Okay, so let's go back and re-explain this equation fully, just to make sure we've all got it. Enthalpy can be defined as the internal energy of a system. So it's interchangeably sometimes used with heat, but in truth, it's not a value you can just measure in an absolute number. You can only measure enthalpy change, which is the change in energy between one state to another in a chemical reaction. We typically notate this in joules per mole, kilojoules per mole, and when it's in per mole, we refer to it as standard enthalpy, which is why you typically see delta H with this little circle and a line through it. This means we are talking about standard enthalpy, and it's in terms of per mole. So, when we talk about enthalpy change, you should know there are both positive and negative enthalpy changes. Can I get in the chat which of those correlates with exothermic and which of those correlates with endothermic? Positive or negative enthalpy, which is endo, which is exo? And yes, Jared, this will be uploaded later on once it's over, but it will probably take a fair few hours for it to go up, if not a day or so. Good. Positive is endo. Thanks, Oliver. Thanks, Mitali. Negative is exo. Thanks, Tortoise. And Sushi. Great. Perfect. So, delta H being negative means you have a release of energy into the environment. You should be able to draw the energy profile, where it's a decrease in enthalpy, so it goes down, and this notates a exothermic reaction. On the other hand, you can have an endothermic reaction, which is instead a reaction where the products have gained energy, absorbing energy from the environment, and you have this increase going upwards as follows. So we know what enthalpy is. Then what's entropy? Entropy is a lot harder to understand. Entropy is defined as the total disorder within a system, and that's really vague, to be honest. A lot of people define it as that, but I want you to be able to visualize what that actually means. So there's a lot of ways you can think about what randomness is. The simplest way to visualize it is if you have a box and you have a ball that is exactly the size of the box, how many ways can you put that ball in the box? And I know this is a little bit strange, you may not have heard this before, but I just want you to think about it. If you have a ball exactly the size of the box, how many ways can you put that ball in the box? Not a trick question. How many ways can you put the ball in the box if it's exactly the same size? Be brave. Good, 1. There is one way you can put this ball in the box. If it's exactly the size of the box, you can only put it in 1. So is that order or is that disorder? Is it order or disorder? If you can only put the ball in the box one way, would you consider that to be an ordered system or a disordered system? Yes, it's ordered. If there's only one way to put it in, it's ordered. Now, consider if you now made the box bigger. You now have a really big box. So you have your big toy box from when you were a kid. And you now try to put that same ball in the box. There are now probably 20 different ways you can put the ball in the box across the bottom of the box since it's a solid. This system, you would say now, has a greater amount of disorder. It has a greater amount of disorder, and you could say it has a greater amount of entropy at the same time. So the first way we can visualize entropy is in terms of the volume a system is contained in. The larger the volume is contained in, the larger the entropy. Fair enough. The second variable you can pull is then, apart from volume, you can also consider how much stuff is in the box. So now if you try to put 2 other balls in, you can put the first ball in 1 in 20 ways, the second ball in the other 19 spots, 1 in 19 ways, and the third ball in 1 in 18 ways. That's again more random. So the ways that you can modify entropy, what makes something more random, is firstly a higher volume, secondly a higher mole amount of what you have or a higher concentration. What are the other ways you can change entropy? Can anyone think of them? How else can you change entropy in a system? Stretch your mind back to Mod 4. How else can you change entropy? Heat, good. Temperature. Increase temperature. Good. And to be honest, they're the main things. From a Mod 5 standpoint, the one that matters most is the moles and concentration. Because when we talk about entropy change, typically we're comparing two sides of an equation. If we were to look at, for example, the photosynthesis equation here, which side has a greater amount of entropy? What will we say? The reactant side or the product side? Which side has a greater amount of entropy? Good. Left side, as there's more moles, and to be more specific, it's more gas and liquid moles, since there's the same actual amount of gas moles. So these would pretty much have the same amount of entropy. But then the difference comes about when you're comparing the 6 liquid moles versus the 1 aqueous mole of glucose. And you would say, if this reaction was to proceed, then this would be a delta S that is less than 0. It is becoming more ordered. It is a decrease in entropy. And so we can say this is a reaction that has a negative entropy. Some questions in the chat going back quickly. How to know if dissolution is positive enthalpy and positive entropy is with positive enthalpy and positive entropy is exo or endo. This is in a later inquiry question, so I'll circle back to this question, ask it again when we get to the inquiry question 4 part. And then the other question which I saw before, how does temp affect entropy? Yes, good question. Not so important for equilibria, but if you think about a system that has, again, making it really simple to visualize, again, a box, and you have one gaseous molecule flying around in the box. Say that it's flying around at 10 meters per second, and it occupies 100 different spaces in that second. Just hypothetically, it's not the true number, but just say in that 1 second it takes up 100 different places. You have to place that molecule in space 100 times in every second it's moving around. Now say that you doubled its temperature and you doubled the speed at which it moves, roughly. Now that molecule takes up 200 spaces per second, and it takes up more spaces per second, which means there's more randomness to account for. And so a higher temperature is going to correlate with a higher entropy. And the last thing that we actually should probably mention is that states. States affect entropy, where gaseous states are higher entropy than liquid and aqueous states, which are roughly the same. You can consider them similarly anyway, which is greater than solid. And that's because gaseous substances fly around and take up space. Liquid is confined to a fixed volume and moves amongst itself. And solids just vibrate in their own spaces side to side. And you can see those movements are much less random as you decrease in your temperature. Hopefully that makes sense for those questions. If not, ask again. Okay, let's keep going. There are some laws of thermodynamics that can come up. This, I would say, is relatively low yield. It's nice to have. If you've got time and you're a band 6 sort of stay rank gunning student, take this into your memory. But if you're not, don't worry. And then tying that together, delta H and delta S, all in one equation, is your Gibbs free energy equation, where you have delta G equals delta H minus T delta S. So, what does the equation mean? Free energy is energy that is available to do work. So when you have a delta G, that is less than 0, it means your system has free energy and the reaction proceeds spontaneously. And if that's the case, your reaction will occur on its own. You don't need to add any more energy, it just happens on its own. We know that from mod 4, and then the opposite is, if delta G is greater than 0, then the opposite is true. It does not proceed spontaneously. The development we get in mod 5, beyond also being able to explain the implications of delta H and delta S contributions, which is driving the spontaneity in terms of what is making the delta G more negative. This should be familiar from module 4. If it's not, read up on this. In terms of what the development is in equilibria, we now see systems where you can have delta G being equal to 0 or very close to 0. In a lot of cases, you can establish equilibrium when delta G is not quite 0, but it's very close. So it could be a very small positive number, but it's virtually equal to 0. So dots above the equal sign, pretty much equal to 0, is when you can establish equilibrium. So that means in questions, when you go and calculate delta G's, if you're told the system is at equilibrium, you can set delta G equals 0. And you should be able to explain, if a delta G is 0, why is a reaction endothermic or exothermic, or why is the entropy change positive or negative. So that is the development you get, and you should see questions like this, where you're explaining in terms of Gibbs free energy, whether a reaction is entropy positive or negative, or endothermic or exothermic, based on the fact that it's an equilibrium reaction. And that pretty much rounds out the Gibbs free energy discussion that we'll have today. Does delta G tell us about the extent of the reaction? Good question. No, it doesn't. You can have a spontaneous reaction which proceeds extraordinarily slowly, but typically, in most cases, a delta G that is largely negative suggests that a reaction will go to completion. Actually, sorry, let me rephrase. Rewind 30 seconds. It does tell you about the extent of a reaction. It doesn't tell you about the speed at which the reaction proceeds. So if you have a delta G that is negative, the reaction is going to go to completion, but you don't know how fast it's going to go to completion based on just the delta G. That often is dependent on temperature, other factors apart from just the delta G. Okay, cool. Before I get on to collision theory and LCP, can I just double check again? Can everyone hear me? And on a scale of 1 being not understanding anything, 5 being understanding and happy with the speed, could I just get a comment in the chat? 1, 2, 3, 4, 5. Where are you all feeling at the moment? 5. 5, 5, 5, 5, 5, 5, 5. Good. Okay. Great. Let's keep going. So, moving on then. Inquiry question 2. You have collision theory. You have LCP coming into play. And before we introduce those, you should be able to understand that collision theory is talking about what happens in reactions based on whether a collision is successful or not. You can determine that based on several factors, being concentration, volume, pressure, surface area. These affect the frequency at which collisions occur. So if you have a higher amount of any of these, you will have a higher frequency of collision and therefore higher rate of reaction. You can also talk about collision theory in terms of success rate. So success rate talks about if one reactant collides with another reactant, and they collide together, what is the percent chance that this reaction will be successful? And success rate could be 10%. So maybe only 1 in 10 collisions is successful. And you can increase success rate through applying a catalyst, which we should know provides an alternate pathway with lower activation energy. And so that might increase your success rate to, say, 50%. So now every 1 in 2 particles collides instead of 1 in every 10. And so there's 2 ways you can modify reaction rate, either through frequency or success rate, and the only factor that affects both is temperature. It's more important to discuss the success rate side of temperature, because that has a greater effect than the frequency, but technically it does affect both. Maxwell-Boltzmann curve, yes, you can explain these in terms of Maxwell-Boltzmann curve as well. That is true. And we should be able to explain in any given equilibrium system, we see this pattern later, that whenever you have a disturbance to your equilibrium system, your forward rate does not equal your reverse rate. Your concentrations may not be equal, doesn't really matter. But whenever an equilibrium system has forward and reverse rate which are non-equal, the system is not at equilibrium. Non-equilibrium. It has to shift. And so it does so. In this case, if the forward rate is greater, it does so by preceding the forward rate, decreasing your reactants and forming products, and bringing up your reverse rate because you form these new products. Now, that means your forward and reverse rate get closer, they start to converge, and the same process happens again and again and again and again until eventually you have equal forward and reverse rate, which at this point you would say your system has reached a dynamic equilibrium. Okay, you'll notice as well, the rates are equal non-zero, but you'll also notice that the concentrations have to be constant. Do the concentrations have to be equal at equilibrium? Yes or no? Yes or no? question to explain that curve with collision theory today. Can you explain that? Yes, 100% we can explain that. We'll get to it in the collision theory in just a second. And good, everyone's saying no. You do not have to have equal concentrations to be at equilibrium. They can be anything. They could be equal, but they don't have to be. The same way that rates have to be equal. So all of that first inquiry question summarized there. Questions in the chat, keep them coming. Let's go on to 5.2. Factors that affect equilibrium. You should know LCP inside out. LCP, definitions on the screen. You can have your own definition, but the gist of it is here. You should be able to use LCP to predict. That is a really important key word. LCP predicts. It does not explain. So whenever you're asked questions around explaining how factors affect equilibrium, know that an LCP explanation is vastly different to a collision theory explanation. How are they different? How are they different? Type in chat, and I'll just keep on going with the LCP for a second. So LCP, your structure that I want you to take is number one, there is a disturbance. Number two, the system has to resist or partial counteraction. And that allows you to deduce which way we shift. Every LCP response should take this structure. Every single one should take this structure. Okay, so tortoise, LCP is for direction, collision theory is for rate. You're correct in saying collision theory is in terms of rate, but both of them allow us to determine which direction we shift. LCP predicts while collision theory justifies. Yeah, pretty much. LCP predicts, collision theory is more explains, is the better word than justifies. LCP is about factors that stress and equilibrium. Collision theory is about what makes an increase or decrease in the amount of rate of successful collisions. Yes. Yeah, actually, yeah, that is probably the closest, I'd say. Yes, and Sharina, that's pretty much it. It's about the explanation that collision theory gives you. LCP is simpler, collision theory is more complete, but both will tell you whether you shift left or shift right. So let's look at a LCP explanation so that you know what the baseline is for like band 6 level. Structure is here, disturbance, resistance, shift. An example, the disturbance would be what you change. So say that you added reactants and you increase their concentration, the equilibrium would no longer be at equilibrium because it's been disturbed. Your resistance is saying what has changed and what the resistance will be to that change. So the resistance is acknowledging you've had an increase in concentration of reactants. The resistance must be that the system will shift to decrease the concentration of the reactants. Because you increase them in the disturbance, the resistance will act to decrease them partially. And so that tells you, based on that, because you know you have to bring down your reactants, the system must be shifting to make more products, therefore you are going to the right. And that is your shift, the final step of LCP. LCP is Le Chatelier's principle, which is a predictive tool to explain whether an equilibrium system shifts left or right, or towards the reactants or products. Okay. Does that make sense for everyone in terms of the structure? You would apply the same thing for temperature and volume pressure changes. So for example, if you increase temperature and the system is, let's say it's a endothermic reaction, delta H greater than 0, so the reaction will consume heat if you proceed it in the forward direction. What you can say is if you were to increase temperature, the system will act to resist the change. So the disturbance is increasing temperature, resistance will resist the change, so we have to shift in a way that brings temperature back down, which means we should shift in the forward direction, to the right, because that forward reaction is endothermic. It consumes the heat that we added in, partially resists it, and therefore we will shift to the right. And that logic is applied for all of these different shifts for LCP. Disturbance, resistance, shift. If you go through the structure, you will never lose marks on LCP. An important note is that with any LCP question, you must, absolutely must, if you don't, you lose a mark. You must define LCP for a mark every time. People say the first time you do it in your exam is the only time you need it. For me, I don't want to take that risk. I would define it every time you use it in your Mod 5 exam. Because of the Mod 5 exam, you may as well. The only downside is your timing, so just be careful with time. But that would be the only thing to really stress to you guys. What about for exothermic? Let's run that case as well. So if you had exothermic, let's say delta H is less than 0, that means that if you were to proceed the forward reaction, this would increase the temperature of the surrounding. So let's say we, again, have an increase of temperature of the system. That's your disturbance. So D. Your resistance is whatever will reverse that change and resist it to some extent. So the resistance is going to be a decrease in temperature, whatever brings temperature back down to some extent. And your shift, therefore, is whichever direction is going to decrease your temperature, which is going to be not the forward, because that increased temperature is the opposite. It's going to be the reverse direction, so we instead shift to the left. So if you go through this framework for LCP, it becomes so much easier instead of having to guess each time. Okay, so if the rate of forward reaction sped up, would that make the equilibrium position shift right or left? Just to be clear, this is going to be in terms of collision theory, but if you increase rate of forward reaction, so forward reaction comes up, that means you are now turning more reactants into products than you are turning products into reactants. So your reaction will, your equilibrium will shift towards making products, or shift to the left. I'll explain that again in a second. If you increase the temp in the products, if you increase the temp in the products, if it is exothermic, the reaction shifts to the left to counteract that. No, not quite. So if you're talking about a temperature change, you're changing the temperature of everything in your equilibrium system. Both reactants and products are the same temperature. You can't just isolate one side, because you'd have a mixture inside your system. So you can't just heat up the product molecules randomly and have all the reactant molecules at a different temperature. You're heating the whole system from 300 Kelvin to say 500 Kelvin, all in one go, all the reactants and products. So then you talk about it in terms of which shift will either increase or decrease temperature to enact the resistance that you want. Hopefully that makes sense. And here's the summary page, every shift in one page. Take a screenshot, use this. This is sort of the hack. If you can understand all of these in terms of LCP and explain it, then you're good. Now, a particularly tricky case that came up in actually this year's 2025 HSC is the inert gas. The inert gas. Inert gas case is really weird because there are two inert gas cases, one where you have constant volume and one when you have constant, actually variable volume is a better way to put it. Variable volume. Before I go into that, what is an inert gas? Can we define that in the chat? What does inert gas actually mean? And we can use energy profiles to explain shifts of temperature. We can use an energy profile too. That was also asked in 2025 HSC. Noble gases are inert gases, and more broadly, gases that don't react. So if you're adding an inert gas into your gaseous system, it's not going to react with anything. And the interesting thing that happens, the interesting thing that happens is that if you have a constant volume that doesn't expand and you already have a gaseous system inside, let's say the yellow and green is your gaseous system at equilibrium, and you add in this inert gas that doesn't react with anything, whilst the total pressure increases, partial pressures of the yellow and green gas remain unchanged. And this means that you are not going to have a shift in equilibrium, since equilibrium position is determined based off partial pressures for gaseous systems. If those terms don't make sense, this is sort of, again, at the higher end of the mod 5 difficulty, but look into that. Because it was just assessed in the 25 HSC for the first time, I would expect teachers are going to try and trick students in this assessment with a similar style question. Doesn't it occupy space if at equilibrium, so won't it create change of collisions, therefore changing equilibrium? Great question, Tortoise, and you're actually correct. So you will experience a very slight decrease in rate of reaction of everything, since there'll be some redundant collisions between inert gas and reactant and product, but the equilibrium position doesn't change. Partial pressure in a nutshell, I don't want to get this too much because this is definitely peripheral. Partial pressure is the pressure of a gas in a system if it is the only gas in the system. So imagine you just have this yellow gas and its pressure is, say, 300 kilopascals on its own. At that moment in time, because it's the only gas in the system, this is equal to total pressure, and it's also equal to the partial pressure of the yellow gas. However, if you then add back in the green gas, and say the green gas makes the total pressure, so let's say the total is now 500 kilopascals when you measure it, it means that 300 kilopascals is being contributed by the yellow, and we call that the yellow gas's partial pressure. So it's the pressure if that was the only gas in the system. And then if you were to look at the difference, the remaining 200 kilopascals must be from the green gas. So we would say the partial pressure of the green gas is 200 kilopascals. And the equation is that total pressure is equal to the sum of all partial pressures. Total pressure is equal to the sum of all partial pressures in a system. And then the implication is that you only need to worry about partial pressure in gaseous disturbances at equilibrium. Is it just because it doesn't react with anything and therefore there's no actual change in concentration of PNR? Okay, let's get to the bottom of this. We may as well. So let's now say we add in the inert gas. And let's say we add in a few of these, and suddenly the total pressure is 600 kilopascals. Can everyone type in chat, what must be the partial pressure of the inert gas if the total pressure has now been increased to 600 based on the addition of the inert gas? What is the partial pressure of the inert gas? 100, good. Thank you, Oliver. Thanks, Dragon. Good. 100 kPa is now the partial pressure of the inert gas. And the second question is, has the partial pressure of the yellow and green gas changed now that we added in this gray gas, this gray inert gas? Good. The partial pressure of the yellow and green gas is still 300 and 200 respectively, which means there has been no disturbance to the equilibrium system. That's what the inert gas case gets at. And the question from Sad Duck is that, would we be expected to calculate partial pressure or anything like that? It's technically assumed knowledge from Module 2. I'd say very highly unlikely, like 0.1% chance you get asked on partial pressure to calculate it, but you can definitely be asked to calculate a total pressure using ideal gas law or a similar law from Mod 2. Would your teacher assess that in Mod 5? Possible, but not very likely. If I was a teacher, I'd be setting an exam that actually tests all of Mod 5, not Year 11 stuff so soon anyway. Okay, hopefully that clears up the inert gas constant volume case. There is another case. There is another inert gas case though, and it wouldn't be complete if we didn't go through it, because this is the stuff that differentiates you. This is what the catalyst students learn. This is what makes you go from 80 to 90 or 70 to 80, whatever your goal is in that higher range. If you have a variable volume, what this means is you have this same system, but instead you have it contained within a expandable bag or a balloon. So you have your green gas in here, you have your yellow gas, and then now you try to add in your inert gas. The difference between this system and the one before is that when you add in this inert gas, the bag is able to expand. The pressure will stay relatively similar and the bag expands to accommodate the new gas. So what is this change synonymous with? The addition of inert gas into an expandable bag or balloon. What is this synonymous with? Good. Decrease in pressure. And more directly, it's an increase in volume. Increase in volume / decrease in pressure. Because when you add in the inert gas into your bag, now the bag has grown in size. It's bigger. The partial pressures of the other green and yellow gas now drop because you've increased the volume. And that will mean you have a disturbance in your system. So you can actually have a shift from inert gas addition depending on if it's a bag, or you won't have one if it's a fixed volume container, like a solid box. So beware of this tricky case. Okay, let's move along. I'm going to clear some of these annotations just to look at the catalyst section underneath. It's important to note catalysts do not affect equilibrium position. They only hasten how quickly you get to that position. So this would be a diagram of the concentration versus time. In a system without catalyst, you can see the black lines. System with catalyst, you reach equilibrium a little bit sooner compared to if you don't have a catalyst. But the equilibrium position is unchanged. There are some case studies again that the syllabus mentions. These are equations you should have seen endlessly by now. These are equations you should know just based off hearing these words. And it's definitely fair game for your teachers just to say, for example, aqueous cobalt chloride equilibrium, and you should know how to write that equation. And then the final part of this second inquiry question is on graphing changes to equilibrium in terms of what changes happened. So if we look at this particular graph, we have 3 different changes that have happened, and I want us to go through these together and identify what is what. This reaction is known to be exothermic. So at 1.5 minutes, what change has been made? What disturbance has been imparted on the system at 1.5, first of all? Type in chat. Type in chat. Be more specific. Is the temperature increase or decrease? I want us to be specific. And Kappa Jetty, yes, that's correct. It will increase forward and back at the same proportion, so you end up having an unchanged rates. So we've got some increases in temperature. Oh, hang on, sorry. I don't think you have the equation. That's probably important. Okay, decomposition. That makes it clear. Just to get the equation out for clarity's sake. Z is in equilibrium with X plus Y. So they've told you it's a decomposition. You have to be going from one to another, and we can find that out because Z is moving the opposite way to Y and Z. Okay, so the reaction is exothermic, and that means if the reaction is causing Z to decrease in concentration, Z is decreasing in concentration, that means we are shifting towards the right. And yes, as Dragon and Sathya, you've clarified now, it is in fact a decrease in temperature. Decrease in temperature because that would shift in the exothermic direction. Hopefully that makes better sense. Second change, or second disturbance, what happens at 3.5? What happens here? Volume decrease. Volume increase, volume decrease, pressure increase would be correct. So an increase in volume or a decrease in pressure. You can tell, hang on, sorry, I put the arrows the wrong way. Decrease in volume. Decrease in volume, increase in pressure. You can tell because all the concentrations have increased. It means that the system has been compressed into a smaller space, and that tells you it's a decrease in volume. By proxy, it's also an increase in pressure. It's not an addition of X and Y. Be very careful when all of your reactants and products change at the same time and seemingly in proportion. So everything seems to have gone up by about 50% in exact proportion of a sudden change. This is screaming at you volume pressure. Be able to identify this. This is not an addition of X, Y, and Z separately all at once. This is a volume and pressure change. And then finally, what's happened at 5.5? I'll just answer some questions as you answer that. How can we see it's a decrease in temp for 1.5? Let's explain that too again. So you can tell it's a decrease in temperature because you have no sudden change in concentrations. No sudden change in concentrations, yet gradual changes thereafter tells you it's temperature. That is the tell that it's temperature. You have no sudden change upon whatever disturbance is made. And if you look across the other two, you have sudden changes. You have sudden changes at least in one of the parts. That tells you that's not temperature change. Question like this, it doesn't matter by how much you increase it, by as long as it's in ratio. It does matter, and it does matter if you're given a scale in particular. For this particular graph, if you are given these axes in drawing, you don't have a scale, so it doesn't matter just how high you go if you do it qualitatively, but the parts relative to each other have to be in proportion to the molar ratios for the resistances, and they have to be in proportion for the volume change. So it would be incorrect, for example, to show that the volume change was this, and this, all increasing equal amounts, because in truth, volume change will be in proportion. Whereas where all the concentrations, for example, if the volume doubled, all the concentrations should halve. And so they have to be in proportion for volume change. Then the more important one, which you always will get checked on and is worth a mark, is the proportion of change. And I actually hadn't looked at the proportion of change yet, which updates my equation as to what it is. But you can see here that once you've had a disturbance, let's have a look at the very start again. Let's go back to 1.5. Once you've had a disturbance, you note that X goes up by 1 box, Y goes up by half a box, and Z goes down by 1 box. The ratio is therefore told to you as 2 to 1 to 2. And so that actually helps me to balance my equation properly. It should be 2, 1Y, and 2Z to clarify the equation. Explaining how we knew it was an increase in temperature as well, going back to 1.5, that comes down to the fact that it's exothermic as a reaction. And because we are shifting to the right, Z can be seen to be going down in concentration after the shift. That means the reaction is shifting towards making X and Y, which are the products. And the only way you can do that, shifting in the exothermic direction, is by decreasing temperature. So that's how we know that the first is a decrease in temperature. And the final case is where we have removal of Y, as some of you have already correctly said. You have a decrease in concentration, a decrease in Y specifically. Okay, good. So concentration equals sudden change, yes, and it's a sudden change in one part on its own, one part in isolation, whether it's up or down. That's different to a volume or pressure change where you have proportionate changes of all concentrations at once in an instant. Is the ratio from the spike to equilibrium or from point before spike to equilibrium? So I think what you're meaning is when you're looking at the resistances, for example, at the very end here, 1, 2, 3, should the ratio be from where the spike ends or where the spike starts? And the answer is it should be from the end. So you're doing your resistance from after where the spike is in terms of half a box going up, and then a whole box going down there. Hang on. Yeah, anyway, okay. Okay. What would this look like as a reaction versus time graph? Yep, that's a fair question. For all of these, you would expect that we can do it in terms of forward versus reverse rate. So rate, time. So we'll do it in terms of products and reactants. So I'll just do products as red, reactants as blue. So this is, in an exam context, you want to actually draw the lines on top of each other, annoyingly. So blue is, actually better off saying forward and reverse. Blue is forward, red is reverse. So in the first change, you note that after the initial change, which is a decrease in temperature, we are shifting to the right. So both of the forward and reverse rate should decrease initially. So decrease in forward, decrease in reverse. However, the decrease in the forward rate should be decrease in forward rate should be less than the decrease in the reverse rate, since we are shifting to the right. So I'm going to redraw these lines. Reverse goes down, forward also goes down, but not by as much. So this means at this point in time, the forward rate exceeds the reverse rate, and our system will come back to equilibrium in the middle of these two. So we've established equilibrium at this time point. And then our equal again, our system is at equilibrium, we're happy. Next change happens, we have a volume decrease, which means all of our rates for forward and reverse should all go up, since we have more pressure on both sides, a high concentration on both sides rather. So we have an increase in forward, we have an increase in reverse, and because the reaction is shifting to make more Z, it means we're shifting to the left, which means reverse rate is higher than forward rate. And that means our reverse rate will go to a higher level compared to our forward. And then we come back to a point in the middle once again. Establish equilibrium. And then finally, our last change is a decrease in Y, which is a decrease in the product concentration. Therefore, we have a sudden drop in reverse rate, no change in forward rate, and that is going to allow our system to return to a new equilibrium here. And that would be the rate versus time graph for all of this. Again, something you can be asked for as well. It's a really good question. Okay. How would you actually remove a specific gas? You would react it out. For example, if you had something you can react chloride out of a aqueous solution with, so silver, that can remove chloride. Typically, that's how you would do it. If you'd add another chemical that's only reacting, yes, correct. Thanks, Serena. How can you tell which one? Sushi's question, since an increase in pressure and temp look the same on a rate of reaction graph, they're both forward. If they both favor the same side, how can one tell? You need more info. Correct. You'd need more info than just inspecting a rate versus time graph. For temp, it's what has the higher or lower action. I guess that's true. I'm not sure if that's I don't think that's a question. I think that's another statement. And how did we figure out that the reverse is greater than forward at the volume change? Yes, good question. So we figured it out because we can see that our reaction at 3.5 is shifting to make more Z, as we can see here. If it's shifting to make more Z, it means our reaction is shifting to the left. Shifting to the left, which means that our reverse rate exceeds our forward rate after the initial disturbance. And that's why our reverse rate is notated as higher. Hopefully that makes sense too. Okay, great questions actually, guys. Keep them coming. All right. Cool. Let's move on to collision theory. Mindful of time. So collision theory, we've already sort of delved into a little bit the factors that can affect it. And we've drawn this graph on for all the different shifts you can have in an applied context, so this is just a repeat of what we've done in a more complete context. Structure for collision theory, the same way I told you the structure for LCP, follow this structure for collision theory. It makes it so much easier. Disturbance, number 1. Comparison of forward versus reverse after the disturbance, and that tells you which way your shift is going to be. So, if, for example, let's go back to that case of a increase in pressure. I don't think we've talked about much on pressure. Increase in pressure. Let's say the system is really simple, 2A shifting to make B, all gaseous. Now, explain which way the system is going to shift in terms of collision theory. 3 marks, 4 marks. Number 1, disturbance. We increase the pressure of the system. In other words, we decrease the volume of the system. 2, how does this affect forward and reverse rate? If we have increased pressure, it means we've decreased volume. I like to always think about volume pressure in terms of volume. It's just easier for me. But because we've decreased volume, it means that both forward and reverse reaction rate will increase because you have more collisions between reactants and products in a smaller, more confined space. However, because you have more reactants, there will be and this is the wording I absolutely love, there is a proportionally larger increase in forward reaction rate due to the 2-to-1 mole gas ratio. And therefore, forward reaction rate is greater than reverse reaction rate. That's it. Because once you've done that, you can say, we're going to shift to the right. Because our forward is greater than reverse, we're going to the right. That's it. Done. So 3 steps to every collision theory. What is the change? How does that affect your forward and reverse rate? How are they now different? And that tells you where you're going to shift. Hopefully that makes it simpler, because I feel like it's not explained really well in most school settings. But LCP structure, know that. Collision theory structure, know that. And you can explain any shift for any condition, for any reaction, for any question. It's really straightforward. What was the equilibria shift response structure for LCP? You can click back in the video and go back and see. Okay, cool. So repeat, concentration changes, how to explain it in words. Pressure volume, how to explain it in words. Temperature, how to explain it in words. And then the inert gas case I touched on before, how you explain it in terms of collision theory in words if you wanted to as well. The shifts that we saw in the graph we just drew on as well. And finally, my biggest peeve is when students mix up the mole ratio changes for the resistance. You always have to consider the resistances in mole ratio. And that will help you to, number 1, figure out equations like we just did before, whether the ratios are 2-to-1-to-2 or whatever it might be. And also it helps you in the questions where you actually have to draw on your graph. And these are so common in a Mod 5 assessment, where you have to draw on what the resistances look like, what the initial change is, and what the resistance is after that. So know how to do those questions, and if you can't do them, find some, because they're super common. Questions like these are ones you want to be able to do. Another one here. Okay. Sample responses, steal these. More questions, more collision theory questions. And that's the end of the second inquiry question. Okay, we're halfway through. This document is available to all Catalyst students. And as I said before at the very start, if you'd like this document for free, when you sign up for Term 1 next year, you get all of Mod 5 for free. As soon as you sign up, you get access to it. So if you're keen, go through our website and you can submit a form and we'll get that all sorted for you. But we'll take a quick 1-minute breather here. 1-minute breather before we launch into the second half. Everyone take a quick drink of water, go to the bathroom. I'll see you back in just 1 minute. All right. Start coming back. I'm going to get going again in just a second, 10 seconds to go. If any questions, put them in the chat. And questions in the chat already. Yes, this video will go up on YouTube. It just might take hours to about a day to go up, which is a bit annoying, but it will go up. And instead of collision, can I use KEQ calculation to explain changes in equilibrium? Yes, you can if you're given qualitative data. So if you get given numbers and you want to find which way you're going to shift, that is the only way you can do it. So that's a different style of question. We're about to get into that with KEQ in 5.3 as this inquiry question. All right, let's go. So just checking again, can everyone still hear me? Just a W in the chat if you can still hear. Put a W in the chat if you can still hear. Thanks, Tal. Thanks, Capagetti. Thanks, Theron. Thank you, everyone. Okay, great. Let's get going. So, 5.3, calculating the equilibrium constant KEQ. This is where things start to actually become quantitative in the second half of the module. You need to understand what K is, but also what Q is, and be able to perform all these different calculations that pretty much get repeated in every single exam ever for Mod 5. Teachers may insert one harder calculation at the end of your exam as differentiating material. So if you're in that band 6 level where you're like kind of top part of your cohort, you're really looking for those top marks, this is where you're going to differentiate. This is where you need to put the most work in. However, I'd understand it's not everyone here. If you're in that boat where you're sort of in the 60s to 70s and trying to get up to an 80, or you're trying to really just push from like a band 5 up to a band 6 sort of level, I would say the best use of your time is to understand just the base case of these calculations and know the rest of this module particularly well, rather than trying to bash out tons and tons and tons of calculations that on the day chances are you're probably not going to get anyway. That would be a better use of your time if you're in the 60 to 70 boat. So from a strategy standpoint, there's a fork in the road here. Figure out which one of those you are and tailor your strategy. And yes, you can get quadratics in internal assessments. You can never get it in a HSC external assessment because chem students can't be expected to know the quadratic equation off the top of their head. It's just the way Nessa set it out. Okay, 5.3, calculating the equilibrium constant. First thing to understand, equilibrium expressions. For any given equation, you should be able to write out an equilibrium expression based on the coefficients of each of the reactants and products and organizing them as products divided by reactants, where it's the concentration of each of the products to the power of their coefficient, divided by the reactant concentrations to the power of their coefficient, all multiplied together. So, hopefully that's okay by now. The rules that you have to be really careful of is reactants and products have to be gaseous or aqueous to be included in the equilibrium expression. Pure liquids and solids are excluded and treated as a value of 1. So that's usually why you don't see them in equilibrium expressions. But what I want you all to understand and take away from today in terms of KEQ and Q is actually what the numbers mean, and in terms of where your system lies in equilibrium, either to the right or to the left. So when you think about K is our equilibrium constant, and it's a fixed value. So K is a fixed value for a reaction at a given temperature. Based on how big or small a K is, it tells you whether your reaction is positioned to the right, where you have more products, or positioned to the left, where you have more reactants. And this is a very common style of question your teachers can ask you, just a qualitative assessment of a K value. So let's say that you have generally K is equal to products concentration on reactants concentration. This is a simplification just for understanding's sake. And let's say your K is equal to 1. This implies that your products are roughly equal in concentration to your reactants. And it means that you roughly have an equilibrium position which lies centrally, where you have pretty much the same concentration of products, same concentration of reactants, or very similar. So when your K is close to 1, or pretty much in the range of 0.1 to 10, you can think of it as having a moderate KEQ, and where products and reactants are in similar proportion concentrations. That's the first thing. Now I want you to think about what a large K or a small K means. Let's think about the large K first. If you have a large K, does that mean our system is positioned to the right or positioned to the left? Is our equilibrium position to the right or to the left if we have a large K? Good. More carbogetic, almost more products, so to the right. Because if you have more products, it means you would be to the right. And it would be to the right because you have more products. So products being a bigger number than the reactants means you have a big K value. That's what K is used to interpret. Then on the other hand, if you have a small K, it means you have much larger amount of reactants versus products. And instead, your system is positioned to the left. So if you understand that, K makes a lot more visual sense. And as you can probably already tell, I'm a very visual learner. I think it makes things a lot easier when you can see it. But yes, this is what we're trying to get at with K. Is it big, is it small, or is it somewhere in the middle? Okay, so some equilibrium expressions, excluding liquids, excluding solids, some questions, fine. And then we get into the calculation types. The simplest type of K calculation is just substituting values to find a K. You get given concentrations. You have to form the equation yourself in this particular question. Sometimes you get given the equation as well, and they ask you calculate the equilibrium constant. So you just insert all the numbers in, you'll get out of value. Not too bad. Okay. Where it starts to get harder, and I'm already seeing some rice mumble in the chat. Do you use rice table to find concentrations? Yes. What's R? My schooling does ice. R is ratio. So sometimes people like to, in this case, for example, put a R here and say it's 2 to 2 to 1, just so you don't forget the ratio in your change column. That's just all it means when you do rice. And you don't have to do the R. I don't do the R. I think it's fine if you have it in your equation above anyway. Screen's inverted. I'm sorry, I have to figure out a way to fix that next time for Rage Bait. And yeah, rice tables, once you get them, it's okay, but they can be challenging before that. So, you have in any icebox style question, you're using initial concentrations, how they change in a change row, and then your equilibrium row, which adds up your initial and your change. Now, the first type of question that you can really get is a question where you're using an icebox to find KEQ. So, question might read, for example, hydrogen and carbon monoxide react as follows. You get given the equation. 1 mole of H2 and 1 mole of CO are placed in a 4-liter container. When the system had reached equilibrium, it was found that 0.2 moles of CH3OH had formed. Calculate the equilibrium constant for the reaction under these conditions. All you must do is insert your initial concentrations. So for H2 and CO, you can find those by dividing their moles by the volume. You can also find initially your ending concentration of CH3OH, which is, again, moles divided by volume. All these other values, actually the only other value you can find initially is that CH3OH starts at 0 because it's not mentioned. You can then find all the remaining values from finding one change value. You find the change in CH3OH, which is the difference between these two numbers, 0.05. And since everything's in a 2 to 1 to 1 ratio, you can find this change, you can find that change. And that allows you finally to find the equilibrium concentrations of H2 and CO, and finally insert that all into your K expression as shown here to find 11.11. So your first simple type of KEQ question. Some questions in the chat. How do you know in the change column if it's plus or minus for reactants and products? Great question. You know based on whatever change you find first. So if in this case, and typically it's typically going to be this way where you're making products, most commonly your products will have a positive sign because you are making those products in your reaction. The reactants, because you are turning reactants into products in order to make the products, they're going to have an opposite sign since they're being consumed. So a minus and minus are placed in front of our reactants here since it's opposite. And that accounts for those changes. Hopefully that makes sense. If in a Q like part A, for example, makes you establish that the equilibrium favors the reactant side, then in the ice table, instead of subtracting the change for reactants on the ice table, would you add it? Yes, correct. So that's the only opposite case, is if it's favoring shifting to making reactants, which would be a very counterintuitive setup, but it's possible. You just do the opposite, correct. Do you now compare Q and K to see if it favors forward and reverse? Don't jump the gun. We're not there yet, but yes, that's coming very soon. We're not there yet because we haven't calculated a K value. Sorry, we haven't calculated a Q value. This method here has only allowed us to calculate K. Technically, this is also a Q value that's equal to K, but for the purposes of what we've discussed so far, we've only calculated K. Here's a question if you want to try one later, similar style. And then there's another style of question that allows you to use an icebox to find equilibrium concentrations. This setup will be different because you are given your KEQ and you're asked to find concentrations. It's a different setup, whereas the last one you were given concentrations and asked to find the KEQ. This is essentially the reverse. And a special method called the small change assumption comes into play, which gets rid of the need for quadratics, which was mentioned before. So let's have a read of the question before we get into it. Question 27. Nitrosyl chloride decomposes into nitrogen oxide and chloride gas in the following equilibrium. 2NoCl goes to 2NO and Cl. Calculate concentration of nitrogen oxide produced in the reaction when 171 grams of nitrosyl chloride is placed in a sealed 2.5 liter container. The KEQ of the reaction is 2.5 times 10 to the negative 6. Okay, so what do we know? We know what the initial concentration of NoCl is. We can convert that from mass to moles to concentration, and that's all done here, inserting its initial concentration. We also know that we have a starting concentration of products that are both 0, since they're not mentioned, and the next step is the crucial step. We let the change be in terms of x, and we say that the change will be minus 2x, plus 2x, and plus x in terms of the molar ratio of 2 to 2 to 1, and noting the opposite signs because of reactant versus product. And that allows you to find your equilibrium concentrations. What you will notice, however, is that the equilibrium concentration of NoCl has had its 2x taken away. It's gone. And the reason why we can do that is because of the small change assumption. We've assumed that because our KEQ is so small, 2.5 times 10 to the negative 5 or 6, I think it's 10, let's go with 10 to the negative 6, it looks like. Remember what we said about a really small K value. If our K value is really small, think about it a second. What does that mean? It means that we have extraordinarily small product concentration. And our system is far favoring reactants. So if we let these reactants sit, we're going to make a minuscule amount of product. Literally tiny, like 0.0001 or 0.5 or whatever. But it's going to be a really small amount. And so if you know that's roughly what x is going to be, the change, and you compare that to 1.0449 minus 2 times 0.0005. We don't know if this is a number, I'm just saying, based on the KQ, this is roughly what it would be. We can then go in and say, well, this is pretty much just equal to 1.0449. We may as well just say, because this is such an insignificant amount to account for, we may as well not account for it. That's what the small change assumption is. Okay. And then that allows you, finally, to insert all of your equilibrium concentrations into a K expression in terms of x, equate it to K, and then solve for x, which gives you your concentration of products as what you were trying to find in the first place. Hopefully that makes sense. This is your bread and butter. This is a question I would spend an hour on just revising, doing different types of this question, because it's so common. If you're not on top of this, you will lose marks. That is as straightforward as it comes. Questions. Do you now oh yeah, we already did that. Can you use small chain assumption if KQ is really big, like greater than 10 to the 3? Simple answer is no, if that's in the direction you're going. But if you're using the KQ of the reverse reaction, that is a really big number, then the forward reaction will be a really small KQ, applying that oppositely. So KQ has to be small in the direction that you're trying to proceed your reaction to apply small change assumption. That's the take home. What if KQ is big? Then do we do it with the values without removing them? It shouldn't ever be this case. As I said, NESA can't make you use quadratics, but you can't use small change assumption if it's greater than, say, 10 to the negative 3 really is where it gets dicey. And it also depends on the concentrations too. But if KQ is big, then you can't use small change assumption, and you would have to do a quadratic. Most of the time, the setup won't do that though. Most schools are just going to get you to use a small KQ value. Okay, cool. Now, we've done all the KQ common question types, but then there's Q. And this is where everyone gets completely mind blown, because Q is completely different. And I think it's very easy to get hung up and confused, because the common confusion is Q has the same expression as K. Q is the same expression as K, exactly the same. So how can it be different? The key difference is that Q is an experimental value, whereas K, I'll just do it on top, K is a constant. So for any equilibrium system, whether it's at equilibrium or not, if you take all the concentrations of reactants and products and you put it in the expression, you have calculated a Q, because you are experimentally testing what the expression is equal to when you put in those concentrations. You're calculating a Q, whether you're at equilibrium or not. You are only going to be equal to K if your system is at equilibrium. And so then the whole big point on comparing Q versus K is that based on whether you have one of 3 cases, you can say you're going to shift right, shift left, or not shift at all because you're at equilibrium. And those cases are as follows. If your Q is bigger than your K, think about it logically again. If your Q is bigger than your K, do we have more products or more reactants than we need? Think about it. Q being big means we have lots on the numerator, less on the denominator. Lots of product. We have too much product. In order to shift to reach equilibrium, we need to consume some of the product, hence we shift left. That is the first case. If Q equals K, it means we're at equilibrium, nothing happens. Concentrations are perfect. And if Q is less than K, again, think about it logically, it means we have too much denominator, not enough numerator. Hence, we have too much reactant, we have to turn reactant into product, we are going to shift right. That's the 3 cases you can have when you compare Q versus K, and you arrive at the end of this style of question, which might look like this. You get given 3 mole amounts, you're asked to figure out, are we at equilibrium, which way do we shift, plug all the values in, compare it against K, and in this case we find the value of Q, this should be Q, is 1.46. It's a lot smaller than K, therefore we have too much reactant, therefore we're going to shift to the right to increase products, decrease reactants. Okay, cool. Another question here if you want to test yourself, and a challenge question as well, combining a few of those concepts we've just talked about there. So, before we launch in this last bit, some questions in the chat. If you haven't done SCA at school, I'd be concerned. This is really important. Really important. KQ is big. Yeah, we already did that. It may well have been MCQ 20. I don't have perfect memory of the question numbers, but I'm pretty sure it has come up in this context. Square root rule. Not sure exactly what's meant by that. It may just be referring to when you're solving for x. I think that might be what you're meaning. Yeah, so to quickly reiterate the difference between Q and K, when you take any set of concentrations, so let's go to this question here. Okay. We have some gas amounts in a system, and we can turn them all to concentrations by dividing by the volume, and that's what they do in the answer. So they find all of these gas concentrations, right? When you take those random concentrations, these experimental test, completely random in a fixed moment of time concentrations, and put them into the equilibrium expression, what you get out is a Q value. Q being the experimental test number. At that particular point in time with those concentrations, what's the equilibrium expression equal to? And chances are your Q won't be equal to K. Your Q won't be equal to K, which means that your system is not at equilibrium. That's what we mean. And K is just this fixed number. There's only one thing it can be equal to for a reaction at a set temperature. And when you compare Q versus K, based on the three cases that we talked about just before, you can figure out whether the system's at equilibrium or whether it needs to shift to the left or right to establish equilibrium. Okay. Yes, we actually have a lot. I have the Mod 5 assessment predicted questions at the very end, and I have some curveball ones in there that I'll go through at the very end of today, so stick around till then. Q is just same as K calculation, but use the initial concentration. Yeah, pretty much. Thanks, Safia. I don't know if I'm saying right. Satyavel. That's exactly right. So you're taking initial concentrations and just inserting them in to test them. Can you always assume for these questions that the systems are able to reach equilibrium? If it's well, yes, they'll always be able to reach equilibrium if it's a equilibrium system, which is what you're given in all these questions. It'll just take time to reach that point. So yes. Oh, right, okay, I see what you mean. B, C, yep. Yes, that is one way you can do it. It depends on the question type. It has to be a specific type of question to do that, though. Okay, cool. So then, finally, the conclusion to all this K and Q business is there are different factors that can affect K and Q. Now, the simplest way to understand this, simplest way, we've already talked about all this. The simplest way to understand this is that Q, which is determined by your initial concentrations, can only be affected by factors that cause sudden changes in concentrations, i.e. concentration, a sudden change in one of your reactions and products, or volume and pressure, a sudden change in all of your reactants and products. These will change your Q value, and it means that after you change the Q, for example, if you were to make Q bigger by adding more product, your Q would no longer equal your K. And if you imagine on a number line, initially when you're at equilibrium, K is equal to Q, and I'm going to try to do my best to reverse the mirroring here. If K is equal to Q, and then you increase your products, your Q is going to increase to a larger number. So Q is no longer equal to K. Your system, therefore, is not at equilibrium. The shift, which tries to reverse the initial change you made and counteract it, is going to decrease your Q. By turning more products into reactants, shifting to the left, your Q comes back down because you're making more reactants until Q equals K. New equilibrium is established. And this is the final piece with equilibrium understanding. You're able to explain it in terms of LCP. You're able to explain it in terms of collision theory. You can explain it in terms of your like K versus Q just numerically, but actually understanding the way Q moves and the way K moves in temperature change is the final piece. And the final piece is then K is only affected by temperature. It's the actual change of the constant you're comparing against to be at equilibrium. So again, at equilibrium, Q versus K, say you have an endothermic reaction and you increase temperature. If you increase temperature, your K is going to get bigger because you are now, your equilibrium position is going to be further towards the right, further towards more products, and so your Q is no longer equal to K. And it's never K that moves in a resistance, it's always Q that moves in the resistance. So Q is not equal to K, Q is going to rise up until it equals K by making more and more and more products. And so you can visualize them both once again, Q versus K, understand what changes Q, understand what changes K, and you can now also justify shifts in equilibrium in terms of Q versus K. And that's it for this little bit. There's a few dissociation, or there's some KQ applications, dissociation we're about to get into, and then acid-base dissociation, KAKB. This is Mod 6 coded stuff. For the most part, your school shouldn't test you on Mod 6. Some schools go ahead and do a little bit of Mod 6 at this point, and if that's you, should do a little bit of study around these calculation types. But for most of us, we're not going to see KAKB in our exam, and if it is, it's in an applied context, you can figure it out in the exam. That'd be what would happen. This is a weird and wacky one. I don't want to talk about this because it's so left of field and so rarely assessed at this point in the year. It's an overlap from Module 8, which allows you to find a KEQ from a practical investigation. If you've done this, know how to do this prac. But if you haven't done this, don't worry about it. You can go back and watch last year's explanation of this in the rapid review, or you can even watch this video here. I know it's a bit of a trek to copy it out, but this was from another channel on YouTube, which is pretty good. But that's all for inquiry question 3. Quick summary at the end, and we're on to the home stretch. Okay, so questions in the chat. What have we got? Can we do solubility tricks once we get to them? Yes, we're about to get to them. Inquiry question 4. Nagsag, Castrobet, good. That's exactly right. Could you explain how you would estimate changes to the KEQ with a temperature change using LCP? Yeah, I guess we can do that. I'll do that quickly. So let's take that case we just had again. This one here. So because you need to know which way you're going to shift first before you can figure out what is happening to K. So we know that the reaction is endothermic in the forward direction, let's say. So delta H is greater than 0. Let's say we increase temperature. So disturbance, increase temperature. Resistance has to bring back down the temperature a little bit. Therefore, our shift is going to be in the endothermic direction because that is the one that consumes energy, brings temperature down. So therefore, we're shifting to the right. Okay, hopefully that makes sense from LCP. Now that you know that you're shifting right, it means that Q is somehow becoming bigger. It's making more products. And that means the only way that we can have a Q that's moving to the right is if K had moved to the right from the temperature change. So K got bigger, Q follows K to reach a new equilibrium. And that's how we can figure out using LCP whether K or Q got bigger or not. Depth study. Oh, right. This practical investigation, or the one I just mentioned, yeah. I would have a watch back of last year's review. I don't want to talk about today because we're a bit short on time and it's not super high yield. Okay, cool. That's all the questions for now. Let's get into the final inquiry question, which is solution equilibria. Question being, how does solubility relate to chemical equilibrium? The questions or the topics you need to be able to really answer well. Again, going through the big headings, ionic dissolution. This is just one of those topics that students really struggle with all the way up until the day of the HSC, and for no good reason, because it's a topic that relates a lot of year 11 concepts into year 12 with intermolecular forces, and it shouldn't be something that is as confusing as a lot of people find it to be. So, first of all, we have to go back and determine what is it we're actually trying to explain. We're trying to describe how a dissolution of an ionic compound in water occurs. This occurs by the formation of intermolecular forces between the water and the ions that you are dissolving. Intermolecular forces being forces between molecules. So this is your dispersion force. Dispersion, dipole, hydrogen bonding, ion dipole, are all intermolecular forces. And an ion dipole interaction is something new that we introduce here. It's the interaction or attraction between a ion, say a positively charged ion, and a negative dipole. Hence ion dipole. Or it can be negative ion to a positive dipole. Again, ion dipole. And a dipole, to define that fully as well, a dipole is a partial charge that is induced from either deficiency or excess of electrons around a particular atom. Okay, cool. So how does dissolution work? You can sort of think about it in 3 phases. You have 3 distinct phases that occur in an ionic dissolution. You have the breaking of hydrogen bonds between water, the breaking of ionic bonds between the ionic lattice, and the forming of ion dipoles. The order in which you say these is kind of a chicken and egg situation because they all happen at the same time, for more or less. So it doesn't really matter if you say breaking first or forming first, but the point is both happen. You have to understand that when you break bonds, this is an endothermic process. It consumes energy. When you form bonds, it's an exothermic process that releases energy. And that dictates how in a dissolution process we can usually end up relatively energy neutral. By the end of it, we haven't really had that great of an enthalpy change because we release some energy and then we absorb some energy in the reaction, and it ends up to be more or less about the same. Okay, so starting off, first stage is water's hydrogen bonds have to be broken. So typically water is hydrogen bonded together from the positive H dipoles to the negative oxygen dipoles, and the hydrogen bonds form between the lone pair of the oxygen and the hydrogen dipole. These are relatively strong intermolecular forces. You have to apply energy to break them apart, and once you have broken them apart, you have water molecules that exist as lone single entities, like this. This is an endothermic process because you're putting in energy to break the bonds. So this consumes energy. You also have to break apart the ionic bonds in the lattice, the ionic lattice. And this is just depicted as positive and negative ions in alternation in a lattice. Once you break them apart, you have positive and you have negative ions floating around in isolation. And finally, the third stage, which is the actual formation of the solution, is where ion dipole interactions form between the water and the ions. And they form these shapes that we call hydration shells or solvation shells. Hydration shell or sphere sometimes as well. Hydration shell. So this is a hydration shell, this is a hydration shell. And you can see what's happened is you have an ion that is surrounded by water molecules. And what is allowing this to happen is the formation of what we call a ion dipole interaction. Question to everyone: is an ion dipole interaction stronger or weaker than hydrogen bonding? Stronger or weaker? And question in the chat: how to predict if an ionic salt will dissolve exothermically or endothermically? You can do it if you're given the values of enthalpy and delta G. Sorry, you can do it if you're given the values of entropy change and the delta G, but you can't just look at a dissolution and say it's endothermic, or look at a dissolution and say it's exothermic. You have to be given numbers to figure it out. Okay, we've got a mix, stronger, weaker. And it is in fact, ion dipole is the strongest intermolecular force. So it is stronger. than H bonding. Sorry to everyone who said H bonding was stronger. So ion dipole is stronger. You can really logically make sense of it because hydrogen bonding occurs between two dipoles. Dipole to dipole. These are partial charges. Say for example 0.2 plus and 0.3 minus. But then a ion has a full charge or even 2 charge or 3 charge. So you're having a 2 plus or a 1 plus interacting with a negative dipole. We now have a whole 2 charge versus a attracted to a 0.3. It's going to be stronger based on the fact that you have a full charge rather than a partial one. So remember that. If you remember that, you'll never forget ion dipole is stronger than hydrogen bonding. Okay, so explain the process. Why does this matter that we broke and formed bonds? It's because the overall enthalpy change is going to be relatively similar. The initial phase consumes energy, which is not a favorable process. Putting in energy makes your reaction have a reverse enthalpy drive. It's less spontaneous. And so we need something to provide energy in order to make the reaction happen. And that energy comes from the formation of these ion dipoles. This releases energy back into our system, which then can be used to break apart more ions, to break apart more waters that are attracted to each other. And the process keeps on going because you have this consumption of energy, release of energy, consumption, release, consumption, release, consumption, release, and you keep dissolving and dissolving and dissolving favorably because the enthalpy change is roughly similar. And that's what a top level response is going to say. It talks about not just the formation of the intermolecular forces, but the energy exchange and why that's important. Okay, so summary, these are the diagrams talking about which inputs or outputs energy, which is endo or exo, and that is how dissolution occurs. So when you sprinkle your salt in water, this is what's happening to the NaCl in that salt. It's being broken apart, water is forming ion dipoles with it, and the water is also being broken apart in that process too. Alright, so now that we understand how solubility occurs, which is a question you can be asked, 3 marks. How does an ionic compound dissolve in solution? Explain, 3, 4 marks. Include a diagram, it can be the 4th mark. You now need to understand how solution forms an equilibrium and how that's actually different to most gaseous equilibria. So, solubility equilibria occurs for any ionic dissolution because your system will come to rest when the ions are at a specific concentration where you can't add any more solution add any more solute into the solution. And so you establish solubility equilibria from the point where you have a saturated solution. Saturated solution meaning you cannot add any more solute into that volume. It's completely full. Could you say saturation is a point at which the energy consumed is greater than release, so it stops dissolving? Not quite. That's actually a good question. I don't have a perfect answer, but the simple thing is that at that point of saturation, you cannot dissolve any more salt. That's all we really need for our year 12 purposes. So when you reach that point, the system that establishes is you have all this solute dissolved in solution. So I notated as purple. Oh, it's not a great color. Let's do yellow. Yellow, dissolved in solution, and you have a bunch of solute sitting at the bottom of your solution that can't dissolve. And this equilibrium that establishes is AB aqueous, not aqueous, solid, dissolving to form A plus B minus. And it's this constant interconversion between the solid that sits at the bottom, dissolving, and some of the dissolved solute precipitating back out. That's where your equilibrium lies in a saturated solution. And that is also why in an unsaturated solution, we notate dissolution as a one-way reaction, because it's gone to completion. There is no reversal of precipitation coming back out. It's just one way. So all of your AB got dissolved. There is no A plus and B minus turning back into AB. Hence, an unsaturated solution is not at equilibrium. Or you could say it's at static equilibrium technically. It's not at dynamic equilibrium. Okay, then the last case of solution saturation is supersaturation. Supersaturation is a transient state. It comes and goes, doesn't last. It's a state where you have more solute dissolved in your solution than it can actually hold. And when you have supersaturation, the system will try to spit out all that excess solute as solid. So it precipitates out. And so for all the questions where you're getting asked, does it precipitate form? Does it precipitate form? And you're comparing QSP versus KSP, this is the state you're being asked about, the state of supersaturation. You're basically being asked, is QSP greater than KSP? If so, that means your solution is supersaturated. And if so, that means a precipitate forms. And when you precipitate forms, you're bringing products out of solution, which brings down your QSP until QSP equals KSP and you reach saturation again. So know these terms well. Unsaturated, saturated, and supersaturated. 3 crucial terms for solution equilibria. Okay. Someone asked a question about how you can figure out on a... No, never mind. This doesn't actually work for that question. Never mind, we'll leave it. But this question is a good one nonetheless because it asks you to explain how dissolution occurs. It relates it to the thermodynamics of it and delta G, and asks you to calculate it, explain why this dissolution would be spontaneous or why it wouldn't be, based on the delta G you find. Is a supersaturated solution in dynamic equilibrium? It is not at the point of dynamic equilibrium, but it will return to it once it's reached saturation only. So it's not at equilibrium because you have too much product compared to reactant for the system to be at equilibrium. Your reverse rate will exceed your forward rate, and so there'll be a shift back towards making more solid until the rates are equal again. So supersaturated solutions are not dynamic equilibria, but they will shift until they reach a dynamic equilibria once it's only saturated. All the precipitates come out and you've hit that point of saturation again. Okay. Cool. The cycad fruit case study. Annoying, but you have to do it. You have to do this case study. Teachers will assess you on it because it's just one of those dot points you have to be assessed on. 3 marks, easy 3 marks if you know it. The case study is that you have cycad fruit, which Aboriginal and Torres Strait Islander people wanted to consume in the past, but unfortunately it has this toxin called cycasin. And the formula is here, you don't need to know that. You just need to know it's called cycasin so you can reference it in your answer. Cycasin is harmful to human beings when you consume it because it's carcinogenic and neurotoxic. So you have to remove it before you consume the cycad fruit. And the detoxification method uses solubility. It's an application of solubility equilibria. So the method essentially takes your cycad fruit, and there's more in-depth writing, but I'll do a more drawn-out version of this. So your cycad fruit, you start off with the fruit, crush it up into a ground powder to increase the surface area, and place it in a bucket of water. So you have your bucket of water, and you place your ground up cycasin into the bucket of water. This is method number 1. Now, the cycasin will leach out of the cycad into the solution. So cycasin comes out, and you establish saturation with this solution, and no more cycasin comes out. So what you must do is take out all of that water, take the cycasin, put it into a new container of water, and repeat the same process all over again. Reach saturation, tip it out, refresh the water, tip it out, refresh the water. Because each time what you're doing is you're removing the aqueous concentration of cycasin, and the equation you can write would be something like this, or even simpler, you can just say cycasin solid in equilibrium with cycasin AQ. This is totally fine. Every time you remove that saturated bucket of water, you're clearing your cycasin concentration, allowing the system to shift to the right and further leach out the cycasin. So that's method number 1. Method number 2 is you form the same steps. You take the cycad fruit, you crush it up, but instead of putting it in a bucket, you put it into a running stream. Now, when you put it in a running stream and water is continuously passing through, can we establish equilibrium? Yes or no? Can we establish equilibrium in the running stream method? Perfect. We cannot. Pre-ordered the method. I can respect that. I can respect that. So we are not going to be able to form an equilibrium because it's an open system. Matter is being lost constantly, water is being removed, and so every time we dissolve some cycasin and increase our product concentration, our cycasin concentration, it gets removed. We're back at 0. And so you can never form an equilibrium, but what happens is the cycasin keeps getting leached until it's all removed by the stream. The jovial police is out in force. Okay. So that's pretty much it for the cycad fruit case study. The only addition is when you explain this in an explain context, you'd want to explain it in terms of LCP. So you can give the method, you can give the equation, you can explain what happens in the method, but you have to also link it to one of the justification methods, whether it's LCP, collision theory, KEQ, QEQ, but the easiest by far is LCP. If you have the option and they don't specify, just do LCP. It's easier. And yes, the process is called leaching. The dissolution of cycasin into the solution is leaching. Okay, solubility rules. Here they are. Not really much to be said. They just have to be memorized. So they're here. This is a full list. You can also use NAGSAG, Castor-Bear. NAGSAG, Castor-Bear, yep. You can do that. It's not on the screen here. It's what I still use. It works fine for Module 5. It gets a bit tricky in Mod 8, so I'd be careful with using NAGSAG, Castor-Bear when you get there. But these solubility rules are good, and NAGSAG, Castor-Bear works for now. The other hack is you can just check your datasheet, and if it's on your KS list of constants on your datasheet, so if your solute is here, it's going to be insoluble. It will precipitate out to some extent. Okay. They have this throwaway dot point about practically investigating solubility rules. You do it in Mod 3 of Year 11. So if you put two ions, a cation and an anion together, and a precipitate forms, then you can say that the salt that you make is insoluble, and vice versa. If it doesn't form, it's soluble. Okay. For any two salts you combine, you should be able to write the precipitation equation. Your displacement reactions as well, you should be able to write those. And then we get to the very end of today. We have a discussion of KSP, QSP, and common ion effect. The chat is going crazy. Alright, so everyone lock back in. KSP is the same thing as KEQ, just more specific and to an exact use case, which is dissolution. KSP talks about specifically when we're dissolving a ionic compound, which is why we call it the solubility product, KSP, solubility product. Now, what you'll notice is in a KSP expression, you only have products. Reason because our reactant is a pure solid, so we leave it out. We have the same debate about KSP versus QSP. The difference is that QSP is, again, experimental. You take a given set of concentrations of the products, you put it in your expression, you get a QSP. That QSP may not be at equilibrium. It's just a test value. So then you can only have one value that is at equilibrium, which is your KSP that is set at a specific temperature. It's set, and you compare QSP versus KSP to figure out, are you at equilibrium? If it's, and this is the fun part. when you compare QSP versus KSP, if your QSP is equal to KSP, you are at equilibrium, your system is saturated. That is remember those 3 cases we just did before? Now we can all link it up to QSP and KSP. If your QSP is equal to KSP, your solution is saturated, you're at equilibrium. QSP remains constant. If your QSP is bigger than KSP, it means that you have way too much product. It means that you are to the right of equilibrium. Your solution is supersaturated, and your system will shift to the left to get rid of some of that product. It's really straightforward. And then the last case, this one is the tricky one. So actually this one's not that straightforward. It's different to how Q and K behave. So you remember, for Q and K, if we had a Q that's less than K, we said that we don't have enough product, therefore the system's going to shift right. QSP behaves differently because in a solution where you have a limited amount of salt, and you say you dissolve it all in, and you make your A plus and B plus ions. Once you've dissolved all the salt, you cannot just apparate more A plus and B plus. So if your QSP is less than KSP, it means your solution is unsaturated, and there actually is no shift. This is important. There's no shift when you compare a QSP that's less than KSP, because it just means you don't have enough salt to reach the point of saturation. And that's the tricky one that a lot of people miss. When QSP is less than KSP, you do not shift. QSP equals KSP, you do not shift because you're at equilibrium. QSP greater than KSP, you shift left. You precipitate out. And that's the 3 cases. These 3 link directly with these 3. That's it. Okay. You guys are too kind. I'm doing my best. Hopefully it's making sense, and if it is, that's great. Is there a way to visually distinguish if a salt in water is unsaturated or saturated? If there's crystal at the bottom, is that always supersaturated? Okay. Yes, you can separate unsaturated from saturated and supersaturated, because unsaturated, that's not what I want. Unsaturated will have nothing at the bottom, so unsaturated. Supersaturated and saturated are going to have a little bit of crystal at the very least. If you have crystal at the bottom of your solution that's not dissolving, you know for sure it's supersaturated or saturated. That is 100% certain. But you can't differentiate supersaturated versus saturated just looking at it, because both of them will have a crystal at the bottom. Okay, so is it in dynamic equilibrium with QSP when Q is less than KSP? No, it's not. It's not dynamic equilibrium, it's static, because you would have reached a point where the reaction stops proceeding. In an unsaturated solution, you put in your salt, it all dissolves, and there is no precipitation because there's still more room for more stuff to dissolve in. So your reaction rate forward is 0, your reaction rate reverse is 0. It's an equilibrium, but it's a static equilibrium. It's a bit different. Hope that makes sense. Okay. We are almost there. We're doing really well. Alright. So, molar solubility, we should know, is just the moles of a solid we can dissolve in a liter of solution. So it's in moles per liter. Once we reach the point of molar solubility, that's when we say the solution is saturated. And our calculations that we get are molar solubility calculations, where you're given a specific salt, such as barium hydroxide, and asked to calculate its molar solubility. You do this by taking the KSP from the data sheet. So you have a KSP value that you get from this whole list here. So barium hydroxide, pinpoint where it is, here it is. Barium hydroxide, 2.55 times 10 to the negative 4. And that's the number here. And we perform an ice table to find what the barium and hydroxide concentrations are at equilibrium. A lot of people skip this step, but when you start out and you haven't done many of these questions, I highly advise you start with an ice table to actually understand where these numbers are coming from. So what we're saying is we're assuming that X moles per liter of barium hydroxide will dissolve. Let that be X. and assume that you have no barium and no hydroxide when you start in solution. And so you're assuming in your change that all of your X dissolves, which is why your ending amount of barium hydroxide ends up exactly as 0. That's signifying you've dissolved all of your initial solute. The barium and hydroxide concentrations are going to be in terms of X and in ratio. So plus X plus 2X gives you their concentrations. And that's where these numbers actually come from. Yes, good pickup, Cabagetti. It is 2OH. Thank you. So then, once you have these values, you can form your equilibrium expression, and you are supposing you're at equilibrium to solve for this value. Your barium and hydroxide concentration, you can sub them in as X and 2X. A very common mistake is people will sub in, for example, 2X and then still double it because they think they have to do the ratio and then square, and it gets all messy. The simple rule is, whatever your concentration is, just put it straight in to replace what's in the brackets. Don't mess around by putting 2s, 3s outside the brackets. Just put it straight inside, and your power is already counting for how you multiply it. Sorry, how you do the power. Questions. Then doesn't 2 come? Yes, 2 comes balance equation, correct. I presume that question's fine, Dragon, I'll leave it. And we'll move on to the final part, because once you have all of this in terms of X, you can just solve for X and find molar solubility, which is how much of the solid we can dissolve. That's why it's important to understand why this X, or where this X is coming from. Do the ice table the first time you do this, or do it the next time you do a question like this, just so that you have what you need, you have the understanding of what the molar solubility is. But that's pretty much it. Once you're comfortable, you can leave out the ice table. That's fine. But when you're starting out and you're at this point of the year, it's good practice just to do it. Questions, solutions, QSP. We've already looked at this table. To reiterate, QSP less than KSP, no shift. QSP equals KSP, no shift. We're at dynamic equilibrium. QSP greater than KSP, we are to the right of equilibrium, we shift to the left, and we precipitate out crystal. Finally, 2 common question types using QSP. First, super common, is will a precipitate form QSP versus KSP style question? Really simple. You take your concentrations, put them in your equilibrium expression to find QSP. Is the QSP bigger than KSP? Yes, no, or is it equal? And you can say whether or not you form precipitate based on this table we just had before. That's it. Done. Really straightforward question type. Pray for this one in your exam. It's so easy to get 3-4 marks off these. Question, solution, and then question type 2. Final question type for today that we'll talk through, and I know we're a little bit over time, so I'll keep this one short, but common ion effect. I do not know why, but this is one question type that, again, students just miss from this module. Like, it comes up so often, but it's just missed. Common ion effect, in a nutshell, if you read this question, can everyone just identify the common ion first? When you read this question, what is the common ion? Type in chat. Questions in the chat. Yes, you sub them back in. You know how you do the assumption for when KEQ is very small. Well then, what if it's really big? Yes, so we talked about this before. If it's a really big number, you can't do small change assumption. You have to do a quadratic. But most of the times, your school isn't going to give you a setup that doesn't allow you to do the small change assumption, because the HSC requires that. The NESA requires that in the chemistry paper there can't be quadratic formula. So a well-written paper won't need it. Yes, you'll get the case from the data sheet. Correct. Exactly right. Dumb question. Is it like bio long response where you can just dot point and table? For the right question, yes. But for most questions, no. Like the only questions where you table would be compare questions. And I would advise against tables in most contexts. If you're doing dot points, it's full sentence dot points. And your dot points are like, instead of dot points, I would subheading. That's my advice. where if you have, say, 3 things to say in a response, you would subheading the first thing as like blah, 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 this is what I'm talking about, and then write. And then this is your second subheading, write, and the next subheading, and write. This is what I did for my HSC trials. Teachers love that because it's really easy to see where you think the marks are. And oftentimes, once you've seen enough questions, you know where the marks are. You can tell your teacher, I know this is one of them, one worth 1 for each. Okay. And yes, thank you everyone. It is chloride, is the common ion. Chloride ion is the common ion because you have chloride already in solution. Then you're trying to dissolve silver chloride. And the common ion effect occurs because you have a common ion already in solution, meaning that when you try to dissolve another salt that already contains an ion, you'll sort of visualize it like this. Dissolution to the point of saturation is like running a marathon. So you have your start and you have your finish, right? And your start is where your QSP equals 0. Your finish is where your QSP equals KSP. Okay, I want you to visualize this. What this chloride is doing is that it's giving you the ability to run. Oh, I don't want to give it. Okay, no, I'm going to keep it simple. The chloride already being in solution means you start the race closer to the finish line than you would without it. It means you start from here. Your QSP is still going to be 0 because your chloride times silver is 0 since silver starts at 0. But I want you to visualize it as you're starting closer to the finish line. That's what the common ion effect is doing. And if you have a lot of chloride, you might be starting pretty much at the finish line already. So then you cannot add as much silver chloride if you've already got so much of the chloride in your solution dissolved as the common ion. That is the common ion effect. And to put it in one sentence, if you have a common ion in solution, and this is written here, when dissolving a salt in solution that already contains one of the ions that would be formed, solubility is decreased compared to the dissolution in pure water. That's the common ion effect qualitatively. Any questions there? Comment in the chat. But I'll move on to how you solve the calculation. It's pretty much a combination of what we've done before with small change assumption and then molar solubility as we just did now. So if we look at this question here, molar solubility of silver phosphate with its solubility in 0.1 mole per liter of silver nitrate. So we're trying to dissolve silver phosphate into silver nitrate. We already have silver in solution, which is going to decrease how much silver phosphate we can dissolve. Now for this question, it's asked you to compare water versus the silver nitrate solution, so we can actually see the difference when we do the calculation. In water, you'll just process this as a normal molar solubility calculation we did before. You can see here that they've just shortcutted the whole ice table, but now you guys know where this comes from, the 3x and the x. Sub them in, solve for x, you find the molar solubility in water. 4.26 times 10 to the negative 5. Fine. For the common ion effect part, you need to assume that your silver concentration, again, I'm going to do the ice table for good practice. Silver phosphate, PO4, goes into silver plus PO4. And your initial silver concentration is 0.1. The amount of silver phosphate you can dissolve, you assume, is X. And the amount of phosphate in solution starts at 0 because you don't have any to begin with. So your change in terms of X, assuming you dissolve all of this salt, is going to be minus X. So you end up with no silver phosphate left over. And we should include states. Good practice. Don't leave yourself exposed. Plus 3x plus x, 0.1 plus 3x, x. Okay. Ice table done. To solve this question, sorry, this x doesn't look like an x. X. To solve this question, oh wait, I see what I did. 3x, sorry. Okay, done. To solve this question, you apply small change assumption. Because you know the KSP is 10 to the negative 17. it's a very small KSP. This 3x is going to be extraordinarily small. It's going to be in the magnitude of like 10 to the negative like 5 or 6 or 7. So essentially, you can say 0.1 plus 3x, well, that's pretty much equal to 0.1. And then you can go and solve by inserting into your equilibrium expression. So this is your common ion effect calculation. And all that's left is to solve for the phosphate concentration, which you'll note is significantly smaller than if you were just dissolving in water. And that is the common ion effect. Know this question type well. This is a differentiating type of question. Be able to do it. Sum to practice, solutions to practice questions, and that's it. Okay, we're at the end. I know that we are over time, so I'm going to keep it really short to finish off. Predicted questions. We've already talked through all of this today. We've talked through all these questions already, but just to reiterate what I would focus on in your last days, these. Be able to do LCP and collision theory explanations to full mark level for temperature, pressure, volume, concentration. Be able to draw your concentration versus time graphs and actually add on as well your rate graphs too that we did today. I cannot reiterate enough your practical skills. A lot of you have prac exams this term, I know. And also, given the flavor of the 2025 HSC paper, there was so much practical skill assessment. So be able to do all parts of a scientific write-up, whether that's discussing, so validity, reliability, accuracy, error, be able to write your method, be able to do risk assessment, identify equipment that you need, that kind of stuff. It may seem really basic, but genuinely it comes up so much at this stage of the year. So don't miss those things. Be able to identify an open versus closed system and how that relates to equilibrium, as we talked about today. Gibbs free energy equation, needless to say, what that means in terms of whether your system is spontaneous, not spontaneous, or at an equilibrium. Or the psychiatric fruit case study, be able to talk about the method and how that relates to equilibrium justified in terms of LCP. Write equilibrium expressions and apply them in your K versus Q calculations, your calculation of K, calculation of equilibrium concentrations, as we discussed already. Be able to explain how an ionic solution forms in terms of intermolecular force and in terms of the thermodynamics as well. Calculate KSP and QSP. Talk about what it means to have a QSP that is big or small, and talk about the three cases: QSP less than QSP less than KSP, QSP equal KSP, QSP greater than KSP in terms of unsaturated, saturated, supersaturated. And very finally, your molar solubility calculations. I'll write that too. That's probably important. Molar solubility and your common ion effect calculations. And finally, your differentiating questions that we've talked on today. If I was to look at two questions from last year's paper before your Mod 5 assessment, I would look at the inert gas question. We talked about that today. So question 30 from 2025. And I would have a look at the precipitation formation question as well, question 32. That was the hardest question from 2025. You can have a look at our the worked solution that did of that about 3 weeks ago. Just click on our channel. You can go have a look at those questions, just scrub to where they are, question 30, question 32. Be able to talk about temperature change and equilibrium in terms of activation energy. Common misconceptions around this all the time, so be able to do this. We didn't talk about it much today, but research this if you don't understand it still. That iron thiocyanic colorimetry experiment, if your school's done it, know it, because that could come up. And then if you've started on Mod 6 already a little bit, you may get some Ka, Kb flavor into your calculations, but it should be an applied question that's doable within the realms of Mod 5 understanding alone, if it's a Mod 5 based assessment. So that's my predictions for your exam. Generally, for a Mod 5 exam, marks are quite high because there's not really that much you can get challenged by apart from hard calculations, and for a hard calculation, everyone's going to struggle anyway. So again, to reiterate, if you're at that band 6 high top part of your cohort, calculations is where I'd focus in these next few days to weeks. Assuming you've got your content all down and understanding down. If you're at that band 5 level and you're looking to push up from like 60s and 70s up from there, or 50s even, focus on the content, focus on the understanding. Don't worry about the calculations as much. know the basic ones we talked about today, and just leave the high band 6 state ranking level calculations off of your plate, because it's not going to help. And that's pretty much all. If this was helpful today, at all, and you think that having more help like this and more resources like this would be helpful, our term 1 starts in January, 21st Jan, and if you enroll for that before December the 8th, which is, you still have 2 weeks to do so before your assessment, the moment you enroll, you get access to all of our Mod 5 stuff. So these notes from today, you get access to them. You get access to all of our module compendiums, which are syllabus dot points, sorted questions, all of our exams, all of our homework booklets, all of our support, in class, out of class. We still have some drop-in sessions running, and then you get access to our essentially concierge. You can ask us questions throughout the week and we answer as quick as we can. Submit marking as well. You get access to all of that for free for the remainder of this year, and then you'll join us for term 1 and hit the ground running with a massive, massive head start. That's pretty much all. I think to just quickly explain what we do in case you are interested, we teach you content for each term 3 weeks at least in advance for when you learn it at school. So for next module, module 6, we'd start January 21. You start school, you've already finished 3 weeks of content. We'd finish content in week 2 of term for mod 6, and you've done all of this content within a little bit of your holiday and the first 2 weeks of term. So that way you're not sort of floundering when it comes to assessment, trying to get coverage of content. You've done it so early that you're doing questions from week 2 of term, and even earlier than that. And by the time your assessment comes, you're just winning because you've done so much more work than your classmates. You know more questions, you know all the traps and pitfalls you can fall into, so you prevent them from an earlier stage. That's all it is. It's not complicated. And obviously you have access to our tutors, so myself, our other super talented tutors who all have achieved 95 plus in HC Chem, and then our student performance team who manages all your marking as well. So that's all provided for you as part of our program. And you can find out more information through our website, which is www.catalystchemistry.com.au. You can find that in the description, you can find it in our social media bio, and you can submit a form there if you're interested. But that's all for today. If there's any final questions, send them to us on Instagram, because I'll probably end the live in just a second. Thank you so much for sticking around to the end for those who have. And if you enjoy this one, we'll see you at the next. See you then.